Now this question says, assume that potential energy of a diatomic molecule is given by two terms composed of binding energy terms. So you see this says potential energy is given by two terms, one term that corresponds to binding energy. I think you are able to see this one. So this contains binding energy term, and binding energy is given by B by RQ. So this term, binding energy term, is proportional to B by RQ, and a short range repulsion term, and there is another term that contributes to the potential energy, that is short range repulsion. And short range repulsion is given by this term A by R to the power 5. This is a repulsion, this is a binding energy term. Of course, the binding energy term is a energy loss, and the repulsion term. So potential energy is given by these two terms, where R is the distance between the atom. R is the distance between the atoms. So this is a diatomic molecule. R is the distance between atom. Now this says, let me write, so this is a attraction term and this is a repulsion term. So this energy is basically attraction. So attraction energy, attraction term, that is a loss of energy, release of energy. So this will be negative and this will be positive. So the question also gives you the energy EUR is given by A to the power R to the power 5 minus B divided by RQ. And there is a plot that is also given. So plot is given to you. So if you you can plot this graph, because you know the potential energy function. You can plot this graph, and let me see, plot is given to you, so there is no need to plot. So on the y-axis you have potential energy, on the x-axis you have distance from nucleus, distance between two atoms. Now if you consider this term B R to the power Q, so this term will vary something like this. So if I plot a graph for minus B R to the power Q, this will be something like this. Now if you plot A to the power R to the power 5, we will have something of this kind of diagram. So this is AR to the power 5. So this is AR to the power 5. Now if you combine these two functions, so there is a total function, this plus this, if you combine, this will be something like this. Are you getting? So this is something like this, a combined function, and there is a value R naught. At that point potential energy will be minimum also. So this at R naught potential energy is minimum. So this is the combined graph. Now question says, first part of the question says, find the equilibrium point. So you have to find R naught and the force constant between two atoms. Equilibrium point you have to find, and you also find what is the force constant between atoms. So force constant. And the second part of the question says, what is the oscillation frequency of molecule if the mass of each atom is m? So you have to find frequency. Let us find frequency, that the time period, you have to find time period. So we have to find frequency, second part of the question. So if I find time period, that will be fine, because time period and frequency is related to 1 by t is equals to frequency. So let us first find equilibrium point and then we will discuss time period. So how the equilibrium point we can find? At equilibrium point, force should be 0, so Fx should be 0. So F as a R, Fr should be 0. Now this is the condition of equilibrium. So let us say this one. So Fr is equals to 0. And now, or you can say potential energy should be minimum, because Fr is given as minus del U over del R. And this is equals to 0. This means either I can say the same condition d over dr is 0. So I can say in the same condition U should be minimum. So that is also the same condition for U to be minimum. So when equilibrium position, you have two things. Either you can say force is 0, or you can say U is minimum. Are you getting? The same thing. Now U, you know, basically U is given to you A r to the power 5 minus B r to the power q. Now let us differentiate this one. So du over dr. You can differentiation yourself. So let us differentiate. I am writing the differentiation 5a r to the power 6 plus 3b r to the power 4. And this is equals to 0 at r is equals to r naught. So this becomes 0 at r is equals to r naught. So you can say this will be 5a by r naught to the power 6. This is equals to 3b r naught to the power 4. So this will be r naught square is equals to 5a by 3b. Now if you take root, so you will have r naught is equals to under root 5a by 3b. So this is the first part of the question. Equilibrium point, so equilibrium distance is given by r naught is equals to under root 5a by 3b. Are you getting? Now you can also write expression for force. So force as a function of r, this is nothing but minus du over dr. And du I have already calculated. Du over dr is this. So if you take minus, so you will have 5a r to the power 6 minus 3b r to the power 4. So this is the force. Now let us try to see something about SHM. So this is my equilibrium position. So if you see the graph, now this is my equilibrium position. If I displace this particle from here to here, now if I increase the distance between two atoms, so this is the equilibrium distance between two atoms. So this is the r naught. Are you getting? Now if I increase this distance, so let us say if I somehow make this distance slightly larger, that is r naught plus a small r, and that a small r is very small. Are you getting or not? So if I am displacing this with a small r, now this distance, total distance is r naught plus r. Now I am interested in what is the force that is acting on this. If this force is acting in the minus r direction, then I can say basically this is performing in a SHM. So let us try to show this one. So force at, if I displace with slightly distance, so f r plus r naught, this will be given as 5a by r naught plus r to the power 6 minus 3b r naught plus r to the power 4. And now I can write more clearly. So force is given by, so r naught if I take common, so 5a by r naught to the power 6, and this will be 1 plus r by r naught to the power 6. Are you getting? Now here you will have, again you take r naught common, so 3b r naught to the power 4, and you will have 1 plus r by r naught to the power 4. Now if I do binomial expansion, that is very important in this case, r naught to the power 6, 1 plus r by r naught to the power minus 6 minus 3b divided by r naught to the power 4, and this is 1 minus r by r naught to the power 4. So you will have, so if you do expansion binomially, 5a by r naught to the power 6, this is 1 plus nx, so you will have 1 minus 6r, so this is r by r naught, 6r by r naught. Are you getting? 1 plus nx minus 3b by r naught to the power 4, and this will be again, this is minus, this is plus. So I will have 1 minus 4r by r naught. Are you getting? Now if I take common, so you see, if I equilibrium condition 5a r naught to the power 6 3b r, so at equilibrium you see this is the same thing. 5a r naught to the power 6 is equals to 3b r naught to the power 4. You see here. Now if I apply this, these two term will goes 5a r naught to the power 6 minus this, so this two term basically vanish. So I will have minus 5a r and into 6 also. So 5 into 6 into a into r divided by r naught to the power 7. Are you getting? And there you will have minus 3b minus minus plus, you will have 3b into 4r divided by r naught to the power 5. Are you getting? Now let us plug the value of r naught. So what we will have, so let us see, so this is basically, if I take r common, I can take r common, so I will have, and let us take r naught to the power 5 also common. So here you will have 4 into 3 12b plus, are you getting or not? So this will have 4 into 3, so 12b into r I have already taken common, plus, now here you will have 5 into 6 30, are you getting or not? So 30 a, r I have taken common, and r naught to the power 5, so r naught to the power 2 you will have in the denominator, this with a minus sign. Now plug the value of r naught whole square. So r naught is under root 5a by 3b, you see here r naught is 5a by 3b, so you will have, this value will be minus 30a divided by r naught whole square, that is 5a into 3b plus 12b, this into r by r naught to the power 5. So you will have a goes out, so a cancels, so 5 into 30, so 6 you will have, so 6 into 3 minus 18b plus 12b, so minus 6b r by r naught to the power 5. And let us plug the value of r naught to the power 5 r. So now I can say force is equals to mass into acceleration. So mass of 1 is m, and to acceleration, so this is the force acting on any of the particles. So either you can consider this molecule or you can consider this molecule, because this is the force acting, the same force is acting on this molecule as this molecule. So force is equals to mass into acceleration. Acceleration will be d2r by dt square. This is equals to minus 6b r naught to the power 5, and now value of r naught is given 5a by 3b. So r naught to the power 5 is written as r naught to the power 4, that is 5a by 3b whole square into under root 5a by 3b. You can do yourself. So into r. So what we have now, so we will have d2r by dt square, this is equals to minus 6b by m, and this is 5a square, that is 25a square, and 3 into 3 9b square, so on the top you will have 9b square, and here you will have 3b by 5a into r. Are you getting? So you will have d2r by dt square, this is equals to minus, and there is a term 9 into 6, so let me 6, this is a 54 bq into 3b under root 3b divided by 25 ma square under root 5a into r. So if you create this equation by d2x by dt square is equals to minus kx, so this is your force constant, minus omega square x, sorry, so this is minus omega square x, that is omega you can find from here, so omega is root over this whole term. Are you getting? 54b³ and under root 3b, and this divided by, you will have 25ma square under root 5a. So this is your omega. So now if you know omega, you can find the time period, you can find the frequency. And force constant is, and this divided by mass, and this multiplied by mass. So if you remember, so force constant K will be simply, I have to multiply this omega by m, and that will give you the force constant. So force constant, you can verify yourself. Are you getting or not? So force constant will be, so force is simply, so this is the force, you see, you don't have to equate mass into acceleration. So this is the force. So I can say force is K times R. So this is K. So are you getting? So this is the K, and I have to plug the value of R naught. So this is the same thing. If I have plugged the value of R naught, I am getting this one. There is a mass term that is extra. So force constant in this case, you will have 54b³ under root 3b. This divided by 25ma square under root 5a. Are you getting or not? So this is a fairly easy problem you have. So what are the important points we have in this question is, so if you treat this question as a guide for diatomic molecule, you can say diatomic molecule contains two kind of forces. One is attractive, another is repulsive forces. Attractive forces rise in a bonding energy term, bonding energy, potential energy term. Repulsive forces results in a repulsive energy term, that is a repulsive energy term, and they are calling this just short range repulsion term, that is a to the power by divided by r to the power 5. Now the total energy will be sum of these two potential energy. Now you can draw the graph separately to the repulsive term, you can draw the graph of repulsive term, you can draw the graph of attractive term, and then you can add, you can get the total graph. Or if you want, you can also make the same graph, so that the total graph you can make. There is no need to make the separately graph, that is like a repulsive as well as attractive. You can make only one diagram. That is one option you have. Now important point we have in this question is, whenever the potential energy will be minimum, that the force is 0, and at that point of time del U over del R, that is in this case this is only a function of R, so du over dr should be 0. That is the condition of force is 0, or this is the same condition for potential energy will be minimum, and this is the point of equilibrium. If you want to check for this just stable and unstable, then in that case you have to derive d2u by dt dr square. So we are not discussing about this just stable or unstable equilibrium. So you can clearly look the graph and you can say this is a stable equilibrium because this is a minimum position. If you displace from here, this will come this side. If you displace from here, this will come from this side. This is a position of a stable equilibrium. Now to find out the time period, what we have done is we have displaced by a small distance r, and then we have seen the forces. And now this force comes out to be minus k times x, k times r, and if I equate with mass into acceleration, I am getting this k as well as omega values. And these are fairly simple problem, everybody knows. We'll discuss the next problem.